Welcome back. In this lesson, we're going to look at groups of the periodic table, and we're going to look at two really well-known groups, the alkali metals, and then we're going to look at the halogens. The alkali metals are all soft, shiny metals that can be found in group 1 of the periodic table. Here you can see some pictures of each of the alkali metals, with the exception of francium. Lithium here in the top left corner. Then we have sodium, potassium. Then we have rubidium, cesium, and then francium we don't have a picture of because it's difficult to see pure francium, because francium is just really, really reactive and radioactive too. So much so that it's very improbable that you're ever going to see a pure sample of francium and live to tell the tale. All right, so the alkali metals can be found in group 1, and group 1 is the first column on the periodic table. Now, the alkali metals are start with element number 3, lithium, and they go down the column to element number 87, francium. On this periodic table, the alkali metals are color-coded in pink. Hydrogen is also in group 1, but it is technically not an alkali metal. It's grouped in with group 1 because it shares some chemical properties with the alkali metals, and it shares some atomic properties, but it's a gas at room temperature and not technically a metal. So the alkali metals here are group 1 or column 1. As a review, the groups are the same thing as columns, and you can read the group number at the top of a column. There's a number 1, 2, 3, 4, 5, and it goes all the way to group 18, which are the noble gases. So the alkali metals make up group 1 of the periodic table. The elements all have similar chemical properties. They all react with oxygen. They react violently with water. Lithium will even react with nitrogen, which makes up 78, 79% of our atmosphere. They're all shiny and soft, as can be seen in these pictures here. They're all very shiny and soft metals. You can actually cut them easily with a knife, but as soon as you cut them, that exposed surface of the metal will start reacting with air within a matter of seconds. They're all highly reactive with air and water, so much so that they need to be submerged in oil, and they'll be kept in oil to keep them inert and unreacted with anything. They won't react with the oil at all, and so that's what you can see in some of these pictures here. The lithium here is submerged in oil, because as long as it's kept in oil, it's not going to be able to react with air or water. And here rubidium and cesium are kept in a sealed glass tube. Looks like the same thing's going on here with potassium. Okay, so the alkali metals all react with water and air, and if you've seen the video that I posted, it's from the Open University. It shows the succession of reactions between the alkali metals and water, and what you'll notice is that the reactivity of those metals increases as you move down the group from lithium to cesium. We never really see francium reacting, as francium is really radioactive, and as soon as it starts decaying, it actually releases a lot of heat, and it's enough heat that it would be very dangerous and deadly to actually carry out that reaction. So francium is not actually found as a pure sample. Here I've written its half-life is 22 minutes, so in 22 minutes, half of a sample of francium-223 will have decayed. and you wouldn't have any more, and there'd be a lot of heat generated from that radioactive decay. All right, so the question here is, why do you think all the alkali metals have similar chemical properties? And a hint here is to draw the Bohr-Rutherford models for the first three: lithium, sodium, and potassium. So why don't you pause the video and try drawing out those models for lithium, sodium, and potassium. Well, we're back, and hopefully you actually drew them out yourself as some practice. If you draw them out, what you'll notice is that for lithium, sodium, and potassium, the thing they all have in common is that their outermost energy level contains just one electron. The electron that can be found in the outermost energy level is called a valence electron. And if you have multiples of them, you call them valence electrons. But for lithium, sodium, and potassium, the first three alkali metals, they all have one valence electron in their outermost energy level. And the same is true for rubidium, cesium, and francium. And this is what dictates their chemical properties. They all just have that one valence electron, which means when they're forming compounds with other substances, they are going to give away one electron. This one electron is not paired. It's shielded from the nucleus really well. Negative electrons are negatively charged, and the nucleus is positively charged. So this one single electron out in that outermost energy level is very isolated. It doesn't feel the effects of the nucleus. So there's no attractive force between the nucleus and that one electron. Is very, very minimal. So these metals all have an easy time getting rid of that one electron. That electron doesn't really want to hang around that atom very long, and that's what lends a lot of reactivity to these metals. So the thing they all have in common is that one valence electron. Okay, one valence electron in each atom. So let's look at the halogens. Let's see if we can see a similar pattern in their atoms. So here's a picture of three halogens. It looks like chlorine on the left, bromine in the middle, and then iodine on the right. The halogens can be found in group 17, starting with fluorine, and it goes all the way down to element number 117, which by now, this periodic table looks like it came out in 2015. Element number 117 is now called tennessine, one of the more recently discovered elements. It's not called unseptium anymore, it's tennessine. So the halogens are group 17 of the periodic table. Once again, they share very similar chemical properties. They make similar compounds when reacting with other elements. The thing with the halogens is that they decrease in reactivity as you move down the group. So hopefully by now you've had a chance to watch the halogens video that I've posted from Open University. They decrease in reactivity as you move down the group. And reactivity is a bit of a hard to define word in chemistry. In short, you could view it as how easily it reacts with other substances. More reactive things will react potentially faster. They might react with a lot more energy released. Those are kind of the criteria that you would use to determine reactivity of a particular element or compound. All right, the physical properties of the halogens are that fluorine and chlorine are both gases at room temperature. Bromine is a liquid and iodine is a solid. Bromine is a brown liquid at room temperature. Iodine is kind of like a purple crystally solid at room temperature. Both are quite volatile, so in a sample of bromine you'll also notice there's a bit of a brown vapor coming off of the liquid. In iodine, it's a bit of a purple vapor coming off of the crystals. Volatile just means that they turn into gases very easily. If we look at the Bohr-Rutherford models of the first three halogens, what do we notice in common between them? Well, you'll notice that each of the outermost energy levels has 7 valence electrons. So take the time to count them up just to make sure I'm not lying to you, but fluorine will have 7 valence electrons in its outer shell. Chlorine has 7 valence electrons in its outer shell, and bromine has 7 valence electrons in its outer shell. So that means that they all have room for one more electron, which is the reason why they all react to make similar compounds. They react in very similar ways. So the halogens all have 7 valence electrons. Okay? And once again, the valence electrons are the electrons you can find in the outer shell. So whatever energy level their outer shell is in, okay, for fluorine it's in the 2nd energy level, for chlorine it's in the 3rd energy level, and for bromine it's in the 4th energy level. They all have 7 valence electrons. So the principle here is that however many valence electrons an atom has influences the chemical properties of that element. And now the chemical properties are things like how does it react with water? Does it react with air? What kind of compounds does it make when it engages in chemical reactions? So the number of valence electrons are what dictates that, and it dictates what compounds you can form and what formula that compound will have. All right, we're going to see a lot more of this when we start looking at the formation of ionic compounds and covalent compounds. A handy way to remember how many valence electrons there are for the elements in each group is to look at the group number. So for the main group elements, so that's groups 1 and 2, and then groups 13 to 18, what you can do is you can look at the group number to figure out how many valence electrons the atoms will have. So in group 1, so hydrogen all the way down to francium, all of those elements will just have 1 valence electron. They're found in group 1. For group 2, all of those elements will have 2 valence electrons. If you move over to group 13, here's where there's a bit of a trick. In group 13, they don't have 13 valence electrons, they have 3 valence electrons. So starting with boron here at the top and then down aluminum and blah, 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 they will all have 3 valence electrons in group 13. In group 14, all the elements have 4 valence electrons. So that's starting with carbon and then silicon, going on down the group. So with groups 13 to 18, what you need to do is hide the 1 and look at the 2nd digit, and that will tell you how many valence electrons they have. The exception to this is helium, which is element number 2. It will be satisfied with 2 valence electrons. So group 18, it's in group 18, but it can only hold 2 electrons. So that's the one exception to it, but everything else in group 18 will have 8 valence electrons. Okay, the halogens in group 17 will have 7 valence electrons. Okay, so that's an easy and handy way to remember how many valence electrons the elements will have in those particular groups. All right, I'll see you in the next video.